Hey fellow nerds. Today we'll discuss Common Gate Amplifier and Common Drain Amplifier, which is also called source follower. We'll be covering Common Gate Amplifier, Common Drain Amplifier or source follower, their small signal models, voltage gains, input impedances and output impedances. Let us start with Common Gate Amplifier. Here the input is applied to the source. You can see that over here in the circuit model. Output is taken at the drain over here. Let us now figure out the small signal model. For that, first I need the small signal model of a MOSFET. It looks like this. Input is given at the source. Output is taken at the drain. At the drain, we also have a resistor RD whose other side is at VDD. We know in small signal model, this will become the AC ground. So RD can be connected between the drain and the AC ground like this. Finally, at the gate, we have our bias voltage. It will be shorted in the small signal model, so gate will be directly connected to the AC ground. This is the small signal model. Let's take the simplest case and find the voltage gain. All we have in the circuit is V0, the bias voltage, V in input at the source, output taken at the drain, and we also have RD at the drain. Let's take the small signal model. Consider the input loop, I mean this one. I'll start from the ground over here, which is our gate. There is VGS from positive to negative. We have the source, V in from positive to negative, back to the ground. According to Kirchhoff's voltage law, sum of the potential drops should be equal to 0. So in this loop, VGS plus V in should be equal to 0, which means VGS is negative of V in. Now, V out is sensed over here. Basically, V out will be the potential drop across RD. Now, to get the potential drop across RD, we need the current flowing through RD. You can see we have a GMVGS flowing like this. Where is it coming from? Obviously, it has to have come through RD like this. We know current flows from positive potential to negative potential. So RD must have positive potential here and negative here. Now V out is taken over here on the negative end. So V out has to be negative of potential across RD according to Ohm's law is the current multiplied by the resistance GMVGS multiplied by RD. We can write V out is negative of GMVGS multiplied by RD. But what is VGS? It is negative of V in. So negative of VGS can be written as just V in. That gives us V out is GM V in RD. What we want is the voltage gain, which is V out by V in. Easily we can say V out by V in is GMRD. Voltage gain is GMRD. Let's move on and find the input impedance. The first thing we have to do is shut down all the independent sources, which is V input over here. If we shut it down, source will be directly grounded. Now, to find the input impedance, we have to add a potential Vx at the input, which is at the source, and find its relation with Ix, the current flowing like this. We'll start by applying Kirchhoff's voltage law in the input loop again. We'll start from the ground. We have VGS from positive to negative. We reach the source. We have Vx again from positive to negative. According to the law, the sum should be equal to 0. VGS plus Vx should be equal to 0, or VGS is minus Vx. Now, Ix is flowing like this. Since the circuit is open over here, obviously it cannot flow through that direction. Ix has to completely flow like this. But then the current that flows in this part is actually GMVGS. That means Ix has to be equal to negative of GMVGS. Let's write it down. Again, VGS is negative Vx. So negative of VGS is just Vx. We get Ix is GMVx. What we want is Vx by Ix. It is 1 by GM. So the input impedance is 1 by transconductance of the MOSFET. Let's find the output impedance now. Again, the first thing we have to do is shut down all the independent sources, which over here is the V input. If we shut it down, source will be directly grounded. Now, to find the output impedance, we have to apply a potential Vx at the output and find its relation with the current Ix flowing like this. The first and the most important thing you have to see here is this. Gate is grounded. Source is also grounded. That means gate and source are at the same potential, which means VGS, potential difference between gate and source, has to be equal to 0. If VGS is 0, what is GMVGS? It is also 0. So the current flowing over here is 0, which means all of Ix has to flow through RD. None of it is flowing in this direction because GMVGS is 0. Now Vx is the potential across RD. Potential across RD is IXRD. So Vx is IXRD. What we need is Vx by Ix, which is very obviously RD. Output impedance is RD, the drain resistance. Now let's take case 2, where the resistance of input is also considered. As always, the first thing you need is the small signal model. It will look like this. The only difference it has from the last model is that we have R in over here in series with V in. To do this in a simpler way, I am going to use a trick. I am going to call this point over here X, and the potential over here will be called Vx. If I look at the circuit from here through the source, what is the equivalent resistance of this much of the circuit? Well, we already found that. If I look into the source, this much of the circuit can be considered equivalent to a resistor of resistance 1 by Gm. Over here, the only additional thing we have along with V in is R in. So V in is in series with R in, and it is in series with 1 by Gm. Which means we can model this circuit in a much simpler way like this. Before we proceed, I am going to call the point over here X. So the potential over here will be Vx. One more thing, GMVGS will be flowing like this and through R in. We know current flows from positive potential to negative potential. So let us mark positive over here and negative over here. Let's mark Vx over here in the equivalent circuit also. Wait, why do we need Vx? Imagine Vx is our input. Vx is the input that we are directly giving to the source. In that case, what will be V out? If we do that, our case actually simplifies to this, right? We are giving Vx. We are expecting an output. What will be the output? Gain multiplied by the input. Output is going to be GMRD multiplied by the input that we get at the source, which in this case is Vx. That is why I need Vx. I am going to write Vx in terms of V in, so we can find what is ultimately V out by V in. To find a relation between V in and Vx is very easy because what we have over here is a simple voltage divider. So Vx is going to be V in divided by R in plus 1 by Gm multiplied by 1 by Gm. As we already saw, V out is going to be Vx multiplied by GMRD. Now Vx can be written like this. That gives us V out. That gives us V out is GMRD multiplied by V in divided by R in plus 1 by Gm multiplied by 1 by Gm. What we need is the new voltage gain, V out by V in. From here we can easily write that. Gm and 1 by Gm gets cancelled. V out by V in will be RD divided by R in plus 1 by Gm. This is the voltage gain. Let us now solve a problem. We have to determine the voltage gain of the circuit if lambda is equal to 0. Lambda is 0, so we do not have to consider channel length modulation. We have a MOSFET M1 to which input is given at the source. Output is taken at the drain. So M1 is in common gate configuration. Resistance of the input is also considered. Along with that, we have another MOSFET M2 which is also connected at the source of M1. Now, first of all, I'm going to call this point X. So the potential there will be Vx. I'm doing that because once I know Vx, which is the effective input I get at the source of my common gate amplifier, then I can say V out is simply going to be GMRD, which is the voltage gain multiplied by Vx. So to get the ultimate gain of this circuit, all I have to do is find a relation between Vx, which is the potential I get over here, and V in, which is the actual input we are giving. Let us start by marking Vx. Now, as we have already seen, if I look into the source, I'll see an impedance of 1 by transconductance. So this much of the circuit, if I am looking through the source, can be considered as a resistor whose resistance is 1 by GM1. How about M2? You can see that drain and gate of M2 are shorted, which means M2 is a diode connected load, and we already know it can be considered as a resistor whose resistance is 1 by its transconductance. Basically, this much will be modeled as a resistor of resistance 1 by GM1, and this much will be modeled as a resistor of resistance 1 by GM2. This will give us a much simplified model of the circuit, which is this. Again, you can see that 1 by GM2 is between Vx and ground. 1 by GM1 is also between Vx and ground. Basically, they are in parallel with each other. So we can further simplify the model like this. So technically, what we have over here is a simple voltage divider. Vin is being divided between Rin and 1 by GM2 parallel to 1 by GM1. Out of that, whatever is dropped across 1 by GM2 parallel to 1 by GM1 comes as Vx. The rest of the solution is simple. Since we have a voltage divider over here, we can write Vx in terms of Vin. Vx by Vin is going to be 1 by GM2 parallel to 1 by GM1 divided by 1 by GM2 parallel to 1 by GM1 plus Rin. Let us simplify 1 by GM2 parallel to 1 by GM1. 1 by GM2 parallel to 1 by GM1 will be equal to 1 by GM2 multiplied by 1 by GM1 divided by their sum. Or we can write 1 by GM2 multiplied by GM1 divided by GM2 plus GM1 divided by GM2 GM1. Now this and this can be cancelled. So this becomes 1 by GM1 plus GM2. Let us substitute that over here in this equation. That gives us 1 by GM1 plus GM2 divided by 1 by GM1 plus GM2 plus Rin. Let us multiply the numerator and the denominator with GM1 plus GM2. Then we'll get this. Vx by Vin is 1 divided by 1 plus GM1 plus GM2 multiplied by Rin. So we got Vx in terms of Vin. What we want is Vout divided by Vin, which is easy because we know Vout is going to be Vx multiplied by GMRD. That gives us Vout by Vin is GM1RD divided by 1 plus GM1 GM2 multiplied by Rin. This is our gain. Let's go and find the input impedance of case 2, where resistance of the input is also considered. What we have over here is the small signal model that we used. We saw that if we look into the source, this much of the circuit can be modeled as a resistor whose resistance is 1 by Gm. That gave us an equivalent circuit model like this. What we want is the input impedance. So the first thing we need to do is switch off all the independent sources, which is Vin. Now we'll connect a potential Vx over here and find its relation with Ix. This couldn't be more simple. Vx by Ix is Rin plus 1 by Gm, and it is our input impedance. Let us now find the output impedance. I have the small signal model over here. First thing we have to do is switch off all the independent sources. So Vin will be shorted, which means Rin will go directly to the ground. What we have to find out is the output impedance. So we have to apply Vx at the output, which is at the drain, and find its relation with Ix. Before we begin, let me mark the current that flows through RD taking its direction like this. I'm going to call it I naught. If we apply Kirchhoff's current law at the drain, we can see there are three currents. Ix is coming into the node, I naught is also coming into the node, GMVGS is going out of the node. So according to the law, Ix plus I naught is going to be GMVGS. Now let us apply Kirchhoff's voltage law in this loop. We have positive to negative of VGS and positive to negative of potential across Rin. According to the law, their sum should be equal to 0. VGS plus Vrin should be equal to 0, or VGS should be equal to negative of Vrin. Now, current flowing through Rin is GMVGS. So the potential across it is GMVGS multiplied by Rin. Now, current flowing through Rin is GMVGS, which is basically equal to Ix plus I naught. So potential across Rin will be Ix plus I naught multiplied by Rin. So we get VGS is negative of Ix plus I naught multiplied by Rin. I am going to multiply both sides of this equation with Gm. On the left hand side, I'll get GMVGS, but GMVGS is equal to Ix plus I naught. This gives me Ix plus I naught is equal to negative of Gm multiplied by Ix plus I naught multiplied by Rin. Let us open this bracket. Minus Gm Ix Rin minus Gm I naught Rin. We have Ix here, we have minus Gm Ix Rin here. We have I naught here, minus Gm I naught Rin here. Let us group these two terms together and these two terms together. From these two terms, we can take Ix as common. From these two terms, we can take I naught as common. Ix multiplied by 1 plus Gm Rin is equal to negative of I naught multiplied by again 1 plus Gm Rin. We can cancel 1 plus Gm Rin on both sides. That gives us Ix is nothing but negative of I naught. Now, what is Vx? It is the potential across Rd. Current flowing through Rd is I naught. So potential across Rd is I naught Rd. Well, does that mean Vx is equal to I naught Rd? Not exactly. Because we have taken the direction of I naught to be like this. Which means potential across Rd will be positive here and negative here. But we have taken Vx positive here and negative here. So Vx is going to be negative of I naught Rd. But negative I naught is Ix. So Vx is Ix Rd. What we need is the output impedance Vx by Ix, which is Rd. So output impedance is Rd. Let us take the third case. Here for biasing, I have used a voltage divider, R1 and R2. Resistance of the input is included. I also included a coupling capacitor over here. Now, we know the drain current flows like this. For it to have a path to go to the ground, I have added R3 at the source. Let us start by making the small signal model. For that, I will take the small signal model of a MOSFET. Input is given at the source. Output is taken at the drain. RD will be between the drain and the AC ground. R1 will be between the gate and AC ground. R2 is also going to be between the gate and the ground. So R1 and R2 are in parallel. So let us mark them over here as a single resistor whose resistance is R1 parallel to R2. We also have R3 between source and ground. Before we do further analysis, let us simplify this small signal model. For that, I will take the small signal model and remove R3 for now. We have R2 parallel to R1 at the gate. But you can see that the circuit is open over here, which means no current is going to flow through R2 parallel to R1, which means there is no potential drop across R2 parallel to R1. So technically, gate is connected to the ground, or gate is at zero potential. So to make it simpler, let us remove R2 parallel to R1 in the model. Now, if you take a closer look, you can see that what we have over here is the small signal model of case 2. We actually made a simplified equivalent circuit model for this, like this. We saw that this much of the circuit model was equivalent to 1 by Gm, plus there was an R in series with the input. So we got something like this. Now, if we want the simplified version for case 3, all we have to do is add R3. R3 is between the source and the ground. This much part of the circuit model, which is equivalent to 1 by Gm, is also between the source and the ground. So R3 is going to be parallel with 1 by Gm. Let's add it over here. Like we have done before, let us call this point X and mark the potential there as Vx, because ultimately that is the final input our circuit is getting. In the equivalent circuit, it will be over here. Let us now use the equivalent circuit model to find the voltage gain. First, I want to write the expression for Vx in terms of Vin, which is pretty easy. All we have to do is use voltage division. Here Vin gets divided between Rin and 1 by Gm parallel to R3. Out of that, whatever is dropped across 1 by Gm parallel to R3 will be Vx. So Vx is Vin divided by Rin plus 1 by Gm parallel to R3 multiplied by 1 by Gm parallel to R3. This is the actual input our circuit is getting. We know output is GMRD, the gain multiplied by Vx. Let us substitute Vx with what we found. That gives us this. What we need is the ultimate gain V out by Vin. For that, we just have to take Vin to the other side of the equation and we get this. Our gain is 1 by Gm parallel to R3 divided by Rin plus 1 by Gm parallel to R3 multiplied by GMRD. Wait, why did I take GMRD as our voltage gain? Even though this is not our original circuit, we actually have R1 and R2 over here to provide the bias voltage. The reason is this. When we made the small signal model, we saw that R1 and R2 were not doing anything in the small signal model. So we removed them. Once we remove them, then this becomes equivalent to our original common gate amplifier circuit. That means we can use the gain GMRD. Let's now move on to the next configuration, the common drain amplifier or the source follower. Here, input is applied to the gate. Output is taken at the source. You can see the simplest model over here. For the drain current to have a passage to flow through, we have a resistor RL over here. RL is also the load resistor across which we are taking the output. Let us find its voltage gain. As always, the first thing we need is the small signal model. It's going to be very simple. All we need is the small signal model of a MOSFET. At the source, we'll have RL. Drain is directly connected to VDD, so drain will be at the AC ground. It'll look like this. How about we also include channel length modulation? In that case, there will be a resistance R0 between the drain and the source. Let's make this more simple. You can see that RL is between the source and the ground. How about R0? R0 is also between the source and the ground, which basically means RL and R0 are in parallel with each other. So we can simplify the model like this. All I have done is I took R0 from here and I put it instead over here in parallel with RL, because technically RL and R0 are parallel. I can even replace these two resistors with a single resistor whose resistance is RL parallel to R0. Now, I want to make a simplified equivalent circuit model for this. For that, I am going to remove RL parallel to R0 first and find the impedance I can see when I look into the source like this. For that, I have added a potential Vx over here. I am trying to find its relation with Ix, which will be the current flowing like this. This is very simple. If we apply Kirchhoff's voltage law in the input loop, we can see that Vgs plus Vx should be equal to 0, which means Vgs should be equal to minus Vx. Also, we can see Ix is the current flowing like this, GM VGS is the current flowing like this, which means they are equal and opposite. GM VGS is negative of Ix, but VGS is negative of Vx. So we get Vx by Ix is 1 by GM. This much of the circuit is equivalent to a resistance of 1 by GM. Using this idea, we can simplify this circuit model further like this. We have the RL parallel to R0. Output is taken at the source. Vin is over here. Rest of the circuit is equivalent to a resistance of 1 by GM. Now it's pretty easy to find the voltage gain because all we have here is a voltage divider. Vin is being divided between 1 by GM and RL parallel to R0. Out of that, whatever is dropped across RL parallel to R0 becomes Vout. Vout is Vin divided by 1 by GM plus RL parallel to R0 multiplied by RL parallel to R0. What we need is the voltage gain. It is Vout by Vin. We get it as RL parallel to R0 divided by 1 by GM plus RL parallel to R0. Now let's find the input impedance. Assume we have some resistance Rg at the gate. You can see that in the small signal model also. For that, the first thing we have to do is shut down all the independent sources, which is Vin over here. Now, since what we want is the input impedance, we have to apply a potential Vx over here and find its relation with Ix, the current that will flow like this. Vx by Ix will give us the input impedance. This is pretty simple because obviously since the circuit is open over here, no current will flow through this. All of Ix has to flow through Rg. And Vx is connected across Rg. So Vx by Ix is going to be Rg and that is our input impedance. Input impedance is whatever resistance we have at the gate. Let us now find the output impedance. For that, again, we have to shut down Vin. That makes the gate grounded. What we need is the output impedance. So I'll have to apply a potential Vx at the output and find its relation with Ix. Let us apply Kirchhoff's voltage law. We have the ground here. As we go on, we see VGS from positive to negative. Further, as we go on, we have the potential across RL parallel to R0 and then we go back to the ground. Now, potential across RL parallel to R0 is basically just Vx with positive here and negative here. So according to the law, VGS plus Vx should be equal to 0 or VGS should be equal to negative of Vx. Now, let us apply Kirchhoff's current law at the source. GM-VGS is coming into the node. Ix is also coming into the node. There will be one more current flowing through RL parallel to R0. What will that be? RL parallel to R0 has a potential Vx across it. So that current is going to be, according to Ohm's law, Vx divided by RL parallel to R0. So we can write GM-VGS plus Ix is equal to Vx divided by RL parallel to R0. Now VGS is minus Vx, so let's replace it over here. That gives us this. Both these terms have Vx in them. Let us combine them together. That gives us Ix is Vx multiplied by Gm plus 1 by RL parallel to R0. What we need is output impedance, which is Vx by Ix. From here we can easily write it. It is 1 divided by Gm plus 1 by RL parallel to R0. We have Gm here. I am going to write it as 1 divided by 1 by Gm. Imagine this is R1 and this is R2. What I am taking is the reciprocal of 1 by R1 plus 1 by R2, which basically means I have a parallel connection of R1 and R2. If we apply that idea over here, this is technically the equivalent resistance of a parallel connection of 1 by Gm and RL parallel to R0. Vx by Ix is 1 by Gm parallel to RL parallel to R0. And that is our output impedance. We could have also used the simplified circuit model to find our input impedance. It is actually easier. We have V in over here. We have 1 by Gm, RL parallel to R naught. Output is taken across that. What we need is the output impedance. But before that, first we have to shut down all the independent sources. Vin will be shut down. That will make this point directly grounded. To find output impedance, we'll have to apply a potential Vx at the output and find its relation with Ix, the current that will flow like this. Basically, what we need is this. You can see how easy it is to find Vx by Ix here. RL parallel to R naught and 1 by Gm are parallel to each other. And they are connected to the potential Vx. So directly we can write Vx by Ix is 1 by Gm parallel to RL parallel to R naught, and that will be our output impedance. So that's all about it for today. See you in the next video. And please don't forget to subscribe.